This is problem 9-60E. It's on page 518. The load shown in figure P9-60 is carried by a round steel bar having a diameter of 800 thousandths of an inch, so 0.8 inches. Compute the deflection of the bar at the right end. Okay. And actually, I'm sorry, this is a statically determinate beam. I'll get to a statically indeterminate beam in just a moment. Okay, so let's see. Here's the rod. We've got a distributed load all the way along the length of it of 12 pounds force per inch and a 140 pound load out at the end. Okay, it's round cross section, diameter 0.8 inches. Okay, so we want to calculate the deflection at the right end. What we're going to do is use superposition to do it. So go back. In other words, we're going to add up the solutions to two problems. Those two problems are a cantilevered beam with a distributed load on it and a cantilevered beam with a point load on it. So go to page 737, and essentially what we're going to do is use case A plus case C. Okay? So basically, if we want the deflection at the end, then this says that the deflection at the end, by the way, B is at the end. The deflection at the end is negative P L cubed over 3 EI. Okay, whereas the distributed load, if we look at it, that's case C. It says the maximum deflection is at end B as well, and that deflection is negative W, this is capital W, L cubed divided by 8 EI. So basically, if I want the total deflection, it would be YB from case A plus YB from case C. So let's see, from case A, that would be this, negative P L cubed over 3 EI. Case C is negative W L cubed over 8 EI. Let's try I instead of 8. Okay, so now let's plug in numbers and see what we get. Well, I guess we need to get some cross-sectional properties first, also material properties. Did they say it was made of steel? I don't recall.
I just think it's the diameter.
Gave us the diameter?
It's round steel bar.
Round steel bar, okay. Excuse me, so that takes care of E. Let's go get I. It's going to be the first page of the appendices. So page 690. To get I, we'll just do that over here. It would be pi d to the fourth over 64. That would be pi times 0.8 inches to the fourth over 64. And so what does that come out to? 8 to the fourth times pi over 64 is 0.0201 excuse me, inches to the fourth. Okay, what else? Well, we could simplify this just a little bit. This would be negative P L cubed over 3 minus W L cubed over 8 over EI. And so let's see. We need W, which is the resultant of the distributed load. And I forgot to write down the length of that beam.
Well,
Is it 12 inches or 12 feet?
Or no, it's 8 inches.
It's 8 inches? Okay, thank you. So that's the length of it? Okay. All right, thanks. Okay, so that takes care of, now, so if we multiply 8 by 12, that should give us W. So capital W then is 96 pound force. Anything else we need? I think that's it. Yeah, that should be it. So negative P is the load out at the end, 140 pound force. L, 8 inches cubed. minus W, 96 pound force, L, again, 8 inches cubed. I guess I could have put that, I could have factored it out. The first term here has to be divided by 3, the second term has to be divided by 8. Divide the whole thing by the elastic modulus, 30E6 PSI, and I, 0.0201 inches to the fourth, and we should have our result. Let's check the units. This is PSI, so the pounds will go away. Per inch squared, so we'd have inches squared in the numerator, which would give us inches to the fifth, divided by inches to the fourth. Sure enough, this is inches. I'll put the answer up there. So negative 40 over 3 minus 96 over 8, and then multiply by 8 cubed, divided by 30E6, divided by 0.0201. There we go. I got negative 0.050 or so inches, so about 50 thousandths. Anyone agree with that? Okay, so that was a straightforward one. That wasn't too bad. It was not statically indeterminate, that was statically determinate. Notice I did not solve for the reactions at the wall. I'll assume you can do that. It shouldn't be too difficult. Questions?